So good morning, everybody. Welcome. I'm Chris Salvino from Lunar Helium-3 Mining. I'm excited to have everybody attend today's discussion. Our series is entitled From the Moon to Earth, the Trillion-Dollar Helium-3 Frontier. I would like to thank Dr. Cohen, Centarius, Dr. Dummer, and Rachel Zisk for participating in our panel today. The exciting topic today, we're going to be zooming in on tritium versus helium-3, two fuels, two very different fusion futures. This series is about helium-3 from the moon. Each event that we do every month examines a different implication of helium-3. Last month, we looked at the value proposition of why we're going back to the moon. Is it for a public reason, such as Apollo and Artemis, or is there a private issue or a private way to go to the moon? Together, the series as a whole should ask whether helium-3 enables a moon-to-Earth industry. Now, many of you have heard of helium-3, but most of you probably have not. So let's level set on a couple of slides before we get into the discussion. So helium-3 is a rare isotope of helium. It has very special use cases on Earth, and that's probably the most important thing to be aware of. On Earth, it comes from the decay of nuclear weapons production, primarily from the Cold War. It cannot be manufactured at scale, and the estimated US supply is probably less than 5 kilos, which means it's almost gone. The main source of helium-3 comes from the sun. It travels with the solar wind. On Earth, it's captured by our atmosphere, so it never really makes it to the ground. But on the moon, there's no atmosphere, so it's been baked into the lunar regolith for billions of years. The concentration is low, and that's a discussion for one of our mining topics coming up later this year. But the most important thing, there's a rough estimate of 1 million tons of helium-3 on the surface of the moon. That could be a wild estimate. Maybe it's 500,000 tons, maybe it's more. There's a lot of it on the surface. The question is, who cares? Is there use cases for helium-3? And there actually is. There's existing use cases, and the most important is to detect nuclear bombs at borders. Our supply is almost out, so the nuclear bomb detection with helium-3 is actually being reduced. In the future, we have two large use cases coming up. One of them we'll be talking about today is as the fuel source for nuclear fusion. And I would argue when helium-3 is used as the fuel source, we will have the world's first global sustainable green energy source. That discussion will start today. Next month, we'll be looking at quantum computing. Helium-3 is the coolant for quantum computing. Without helium-3, they cannot be cooled down to work efficiently. So there's a lot of supply on the moon. There's use cases on Earth coming up, but it wouldn't matter if it didn't make economic sense to go extract it. So the current price for helium-3 is about $30,000 per gram, plus or minus. That's a rough estimate. That's about $30 billion per metric ton. Now imagine a world in the future. Imagine a world in the future in which fusion was addressed across the globe with helium-3. We would need about 570 metric tons of helium-3 to supply fusion across the globe. That's about $17 trillion in today's dollars. Quantum computing would need about 4 metric tons at about $120 billion. We are starting here and discussing this topic because for more than 60 years, going to the moon, whether it's China, Russia, United States, or other countries, has been a cost center. Governments have supplied the funding to go back to the moon or go to the moon. We believe helium-3 is the only resource plausibly tied to large-scale demand on Earth in which there could be a positive return on investment. We're hosting these conversations because our sole focus as a company is the extraction of helium-3 from the moon. Our questions span space, energy, and economics, and this series exists to explore those questions more publicly. And finally, this series, From the Moon to the Earth, the Trillion-Dollar Helium-3 Frontier, today's topic again is on tritium versus helium-3. For purposes of the discussion, we are going to assume that we've been able to bring back helium-3 to the surface of the Earth. So the focus of the discussion will be on the pros and cons of both fuels for Earth and space-based fusion. And with that, I'd like to turn it over to the panelists and Rachel for the next round of discussions.
Thank you, Chris, for that introduction. And hello to everybody listening in. My name is Rachel Zisk. I'm a reporter covering the space industry. I've also spent a lot of time covering the fission and fusion sectors, focus on business and policy. Very excited to be leading this discussion for us today. I know that we did have bios for our speakers flash up on the screen for a moment, but maybe just to start off, we'll have our speakers give a brief introduction. Um, just very quickly about your background and experience. And then also just a note to anyone that listening in, if you do have any questions for our speakers throughout this conversation, feel free to drop them in the chat. Towards the end, we'll have a little bit of a time for Q&A, and so I will make sure that those get answered towards the end, as much as time allows. So John, I see you up here. Maybe you could give us a little bit of a quick description about what you do.
I'm a plasma physics. That's what burns to make the D-helium-3 or DT fusion. I've been at the University of Wisconsin for 40 years. I'm emeritus now, working on, as it said, clandestine materials detection, like landmines with a neutron source hanging from a drone. I worked in the Fusion Technology Institute at UW-Madison, and in that, most of my colleagues were engineers. So I got, by osmosis, a lot of engineering information that tells me quite a bit about how we do the fusion. And I've been a D-helium-3 advocate ever since we published a paper connecting helium-3 on the moon with fusion energy, both of which had been individually worked on. But the connection of the solar wind depositing it, as you just said, is a different question. That's all.
Thank you, John. Sam, I'm going to go to you next.
Um, I received my PhD doing low temperature physics, roughly at 1 degree Kelvin. And after getting that, I went to Princeton. I've been here 50 years, working on high temperature systems, roughly 1 billion Kelvin. So I've got experience through the whole range of temperature, through a large range of temperatures. I worked on tokamaks for probably 20, 25 years. Part of that time, the last 6 years, was spent on the ITER project. That's been going on now since the mid-1980s. So it's taken a long, long time to try to get the ITER device built and tested and qualified. Because of the major difficulties in the technological aspects for DT fusion, I made a transition to D-helium-3 probably 20, 25 years ago, and I'm very excited because the physics is novel for these devices, so it really is inspiring to study it, and the technology is much, much easier to do. As easy as the physics might be, or as cheap as the physics, the engineering and the practical issues will be very, very important for making any type of fusion reactor work.
Thank you, Sam. And Andrew, last but not least, give us a little intro.
So I guess I'm the youngster, comparatively speaking, in the crowd. So I did my graduate work at the University of Kansas. I did light heavy fusion fission experiments, and then dabbled in some nuclear astrophysics work during my postdoc at the University of North Carolina. But I moved from there into industry, and in my most recent position now, I actually work for a medical device company where we actually do hyperpolarization of xenon 129 for use as a contrast agent in MRI. But I still have, I guess, a passion for doing nuclear instrumentation kind of work. And to that end, I've done work for lunar helium-3 mining. So for a lot of other things to do with the rovers for detection of helium-3 in the lunar regolith, and some of the work in how to collect the helium-3 from the regolith and that sort of thing. So that's my tie-in to this project.
All right, perfect. Thank you so much, all of you, for those introductions. Like Chris said, we are starting from a point in this conversation where we're assuming that helium-3 is accessible on Earth. And we're weighing the pros and cons of using tritium or helium-3 for fusion specifically. We're not going to be getting too deep into the quantum computing cooling side of things today. With taking instead just a focus on fusion and weighing the benefits of using either fuel. We have an audience that could span from all levels of expertise on this topic. So to start off, I'd love to give our audience a little bit of a baseline understanding of the differences between tritium and helium-3 and what they do in a fusion reactor. So could we talk a little bit about how the required plasma temperatures and confinement conditions differ between tritium and helium-3? And just to pick on someone to get us started, Sam, would you start us off?
Sure. In order to get fusion to work, you have to get nuclei to come very close together to overcome the Coulomb repulsion. And that requires giving the ions a very high, large amount of energy. Typically, for fusion conditions, the temperature of the nuclei must exceed that of room temperature by a factor of 10 million. In the conditions we work at for magnetized, magnetically confined plasmas, the density is much lower, roughly 1,000th of an atmosphere. So, nevertheless, the pressure in the plasma is quite high, probably 1,000 atmospheres. The temperature required for helium-3 is roughly 10 times that required by d-helium-3. I'm sorry, the temperature required for d-helium-3 is 10 times higher than required for DT, but that doesn't give me any concern because already in tokamaks they've gotten to within half the amount required for d-helium-3. The energy confinement time would have to be a bit better, the density would have to be a bit better, but otherwise the two are similar in that they both require tens to hundreds of kilovolts of energy, that is roughly 100 million to 1 billion degrees Kelvin.
John or Andrew, do you have anything to add to that
Yeah,
explanation?
let me add that one data point. I agree with Sam. The numbers are relatively that. Usually we use energy unit called the electron volt, like 1,000 electron volts is keV. And 1 electron volt is about 10,000 of degrees with the proper constants. So when we look at the reactor designs, and that's one of the things our group did at Wisconsin for 40 years, is we come up with numbers like 50 to 100 keV for the d-helium-3 operating temperature. That compares basically, as Sam said, from typically around 10 degrees, 10 to 20 keV is what the DT reactors, tokamaks especially, tend to use. There is a data point, though, from, 20 years ago or so, Sam, Jacquinot was doing some what we call radio frequency heating in the Joint European Torus in Cullum, and there was a little bit of helium-3, about 3% in a deuterium plasma, and it's like a microwave oven in many ways, that technique. And he ran the helium-3 component up to 1 MeV, 100 times what DT is doing in this small population. And it was what we call an equilibrium plasma. Things are colliding so that they've come to some sort of equilibrium, and there were basically no deleterious effects on that population. And that's a very useful data point. We should be able to get to d-helium-3 conditions. Things kind of stopped because people got to the DT conditions and said, okay, well, that's good enough. We can come back to some of these issues. I'll give up the floor here.
Sure. Andrew, do you have anything to add just to the comparisons between these fuels actually
level,
do?
I think they kind of hit it between the two. Yeah, exactly. It's a temperature difference, but maybe not as much of an engineering challenge as initially you might think.
Mm-hmm. Sure. So we shouldn't stop when we get to the conditions for DT. We can keep on going to helium-3 without too much trouble. It's an engineering challenge. Moving on, I'd love to also talk about the differences in the safety of each fuel. Talking a little bit about neutron output for tritium, DT, and for D-helium-3 as well. And John, maybe you'd start us off.
Okay, yeah, that's the other aspect to when you're burning these fuels, because you have the energy confinement that's important, as Sam said, the density and the temperature you need to go to. But the fuels produce um, very different amounts of neutrons and charged particles, and to some extent the radiation too. When I say radiation here, I'm talking about bremsstrahlung, which is like X-rays, and we have something called synchrotron radiation, like they do in accelerators. All of those tend to heat the wall too to certain amounts, but in the DT fuel, you've got a neutron and an alpha particle, which is a helium-4 nucleus, that get produced, and it's 17.6 mega electron volts, MeV, and 80% of that energy is in the neutron. And that's why this question is pertinent, is because the neutrons do nasty things, unfortunately. They're very fast. They damage the wall. They knock things about. It's called displacements per atom. And a typical atom in the first wall is getting like 100 or more displacements in a lifetime of the material. And that is worse with the neutrons from DT. And I'm going to skip ahead a little bit to D-helium-3 here. D-helium-3 only gives out a proton and an alpha particle and 18.4 MeV. So very, very similar total amounts of energy coming out. But in the D-helium-3 main reaction, there are only charged particles. But there is deuterium, and interacting with other deuterium in the chamber has two branches, a proton and a triton, a heavy about tritium, and a neutron and a helium-3. And so there are some neutrons that are produced, but basically, depending on what you do with the plasma physics, you typically can get from 1 to 5% of your D-helium-3 plasma energy coming out as neutrons, power coming out. Back to DT for a second, there is a big difference. And actually, Andrew, you probably know this much better than I, but the neutrons, there's a threshold at about 5 MeV. The DD neutrons are only half of that. The DT neutrons are about 3 times that. And above that threshold, you get more penetration by your DT neutrons, and you have other reactions going on that can produce what we call activation, making one isotope into a more radioactive isotope. The DD neutrons do much less of that, the damage. The activation, a lot of it happens once the neutrons have become what we call thermalized back to whatever the material temperature is. And that, a lot has to do with what impurities and what material the device is made out of. But that's a major difference in terms of the damage. So the D-helium-3, basically the structure is going to stay there the whole lifetime, the 30, 40 full power years or something that you would want, whereas every 3 to 5 years, typically the initial about half a yard in from the first wall of a DT reactor has to be replaced. We don't know those numbers completely because there's basically been no experiment that's even got close to the lifetime that the ITER experiment is going to run. And so that's a problem.
Yeah, sounds like that'll be a problem, especially for the commercial fusion sector, having to replace their inner tokamak every couple of years. Andrew, I know that you were called out as maybe having some expertise on this topic. Anything that you'd
Yeah,
like to
so yeah,
add?
it's more like, I think it's about 2.5 MeV only on the DD
Yeah,
for the neutrons you've
2.45.
got. Yeah,
Yeah.
yeah. So,
Did I say
you said
my
about
bad?
5, so I think it's about 2.5.
Oh, no,
But
that's
is it on
DT
the
is
DD?
about neutrons about 3 times that 5
But yeah,
MeV threshold.
yeah. So
Yeah.
DD is 2.5.
Yeah.
Yes. So we forget the D and the T's. Yeah. So yeah, it really seems to me to be the big challenge too is the form your energy comes out between these two reactions. I mean, the bulk of what you get from the DT is going to all be neutron flux, and so we're back to having to harness the energy coming out in a neutron flux. I would think in order to harness the energy, whereas in your D helium-3, you have all charged particles. There's a lot of direct coupling for that to go potentially straight to electricity for use. So that again also is part of the comparison between the two. So you have an engineering challenge choice. How do you harness and how you deal with all this neutron that's coming out of the DT versus, how do you achieve the higher pressures and temperatures required, particularly if you're using a tokamak kind of setup in order to ignite the helium-3 reaction as opposed to the tritium one.
Sure. Sam, anything to add?
Yes, I'd like to add and also modify your question a bit. That as you said, what was the difference in safety for each fuel? Actually, you have to choose the machine as well as the fuel, because the two main machines, the one that can burn DT is called the tokamak, and that is going to be big, roughly 100 feet in diameter, and the FRC would be considerably smaller, whether it's 1 meter in diameter or 3 or 4 or 5 meters in diameter. A smaller machine has a larger surface to volume ratio, so the power load per meter square is much less. In the tokamak, the power load on the wall, due to the neutrons hitting, is roughly equivalent to the power load that an oxyacetylene torch delivers to a piece of steel or whatever you're trying to cut or weld or braze. So the power load on the wall is really critical. There are people who are trying to reduce the damage to the first wall due to the power load by using liquid metals like lithium. So in addition to the safety issue of the neutrons, there's the safety issue of the chemicals being used. Roughly swimming pool volumes of lithium, which is known to be chemically reactive to things like water and air. So those are other safety issues that you have to deal with DT, the materials chemical issues as well as the neutron issues. And again, the heat issues are much harder in a large machine because of the poor surface to volume ratio.
Are there similar concerns with helium-3 with the materials involved in the machine?
No, the materials problems are much less serious for D-helium-3 because the neutron flux, if you can get rid of the tritium, as John said, the DD fusion reaction yields tritium, and so you could end up burning DT in a machine that was meant to burn D-helium-3. So you have to get rid of the tritium that's born in the plasma by the DD reaction. You have to get rid of it very quickly. How quickly? Roughly 10 milliseconds. If you let it stay in there for 1 second, it'll burn up and you'll end up bathing the wall in those same energetic neutrons that are a problem to tokamaks.
Yeah, I would say though, Sam, that it's not quite the same magnitude because you're only producing 1 to 5% of your total power in those neutrons.
Yeah.
But that does raise a question related to the configurations here. And the tokamak is basically a big toroid and huge I sometimes describe them as superconducting cathedrals. They're really big. But the neutrons do have one advantage in terms of the power cycle, and that is that their energy gets distributed and it falls off from the first so-called first wall. It falls off, but it still takes a meter or two of material to it distributes all that energy. So that means when we go from dt, where there's only 1/5 of its energy, or 1/5 of its power in charged particles, when we go to, in a toroidal system, to almost all of the power, and so 5 times the amount in charged particles, those don't get beyond the walls very well. And so we now have more of a heat flux problem, and the heat that has to be taken away if we are in a toroidal system. And that actually is why way early in my career, I got a little frustrated. I had done tokamaks for my PhD thesis also, and more theoretical. But in any case, the systems that, on the magnetic bottle side, if you will, there's 2 types. There's toroidal and there's linear, at least in terms of what the external field is. And Sam works on one that I really like, called the field reverse configuration. The inside is a closed plasmoid, if you will, with magnetic field lines containing the whole plasma, but the external field is linear. And then there are machines called mirror machines that have linear geometry for that magnetic field. Now, what does that mean? It means the charged particles coming out of the ends of a magnetic mirror, or out of this so-called compact toroid in the center of the FRC, like Sam runs in his lab, and then getting into that linear magnetic field, the charged particles are largely going out into some sort of end tank, or if you're doing a fusion rocket, which I hope we'll get to, because I think that's one of the big Helium-3 applications, you can do direct thrust, and that's huge in terms of efficiency, but it also means the distribution of the heat can be much more easily taken in a linear machine. And I think that's all I want to say right at this question time.
So I'm curious though as well, because there are a few other sort of geometries that are under exploration now. I know a company, Helion, out of the Seattle area, is working on a pulse system to produce power. In fact, they're, I think, supposed to be by 2028 going to be going online to supply Microsoft with electrical power.
Helion is an FRC.
So
Helion,
yeah.
The 2 main competitors are tokamaks versus
right, okay.
FRC. They're also RZ.
Yeah, I'm going to talk from their webpage stuff. But yes, Sam is right. They're either an FRC or a spherovac. They could compress 2, but an FRC gives you better starting parameters. Mm-hmm. But what they are doing is they're making 2 FRCs. They could also do spherovacs, slamming them together, and stationary, sort of in the middle of the machine, they make a bigger FRC, and then they're using a coil to try to compress it. It's a challenge, but apparently there's some progress being made there. But then the plasma, 2 things happen. You get fusion, it expands against the magnetic field of the coil, and that puts energy back into the circuit. So they recover some of that energy. They have to do it apparently very efficiently, but nonetheless, then the plasma that gets exhausted is pretty much out the end. Now, you could modify that maybe for a rocket to exhaust it that way, but it is one other geometric approach. And there were, as Sam, you mentioned at the start, I think there's a whole bunch of different configurations of FRCs. There also, by the way, magnetized target fusion comes in a lot of other approaches. Way back in the 60s and 70s, they were doing metal liners compressing some target plasma. They were doing liquid liners, and more recently, they've been doing plasma jets to try to compress things. So there are various, and Sandia National Lab actually takes the whatever is coming in as the so-called liner to do the compression, they magnetize that first. So there's a whole different bunch of ways to do what are called magnetized target or magneto-inertial fusion.
While we're on the topic of these different geometries, I'd love to get back to the talking about these fuels. So, to your knowledge, are there any commercial companies or experiments that are working towards helium-3 fusion, using helium-3 as a
Well,
fuel today? And what
Helion is one.
geometries might Helion is using? Yeah, helium.
Helion is.
And TAE is also considering it. Their main approach is with P-boron-11, but they've also been looking at D-helium-3.
Yeah, and the situation with TAE, what used to be called tri-alpha, because that's what P-boron-11 puts out is charged particles. But that if you can do a P-boron-11 reactor, you have to have some more shielding for the magnets, but you could burn D-helium-3 in it for sure. And the reason that they have gone after P-boron-11, like several other companies have in the past, is that it's much more available on Earth. But instead of like 100 keV, you need somewhere between 200 to 300 keV to burn that. And it's because the boron has a high Z, you get a lot of X-rays, so-called Bremsstrahlung from operating those plasmas, and it's hard to make the power balance work out. You don't get the same benefit of the charged particles that you do with D-helium-3, where the power balance. Early in my career, I was doing mirrors, so-called tandem mirrors, which are a straight linear section with stuff going on at the end to try to stopper the magnetic bottle. And I was able to do designs with D-helium-3 where half of the energy was available for direct thrust or for direct conversion, and the other had to sustain the plasma. And you can, that's doing the kind of full power and particle balance. As Sam said, it takes more in the way of the confinement, and temperature has to be a factor of 5 to 10 higher.
I'd love to talk about now the kind of the engineering challenges and engineering questions with respect to helium-3 and tritium, comparing them. And Sam, I'm gonna point to you first, talking about what size and output of reactor is ideal for helium-3. And I know the
Well, again, I
size,
think
size and
when you
output.
choose helium-3, I think you have to choose a reactor type. And the reactor type that I like, again, is the FRC. There are FRC companies currently at the billion-dollar level. TAE is one and Helion is the other. There's interest in FRCs in Japan, India, China. The engineering for FRCs is much easier than for toroidal machines because they're linear. So you can think of them as being modular. You can take them apart and put them back together. You don't have linked rings, which are always very difficult to put together or take apart. FRCs, as John said, can come in a variety of types. Some are considered to be 100 megawatts. The types I like are typically much smaller, 1 to 10 megawatts. As such, they're smaller physically, and therefore their applications are broader. You could consider them as power sources in remote sites, power sources where there are natural disasters. For space propulsion, you certainly can't put a tokamak type of DT reactor in space. It would take, we should point that out, that any type of fusion reactor rocket propulsion system doesn't have enough thrust to get you off the Earth. So you have to assemble it in space in low Earth orbit. And in order to assemble a tokamak out there, it would take 100 to 1,000 launches to bring the components up because it's such a massive object. While for a small FRC, you could bring up the components in one single launch. So I think those are the main differences between the technological things. D-helium-3 reactors could be smaller, lighter, and useful in niche applications, easier to test, to improve, because they're smaller and less costly.
Yeah, I think they're the smaller and they're easier for sort of distributed energy production,
Right.
potentially, as
Yeah,
opposed to our model currently, where you have a large generating facility that.
Mhm.
So
yeah. The tokamak is is definitely not a propulsion device, and part of it is if you look at the modern designs, the Commonwealth fusion systems or whatever, they're the ratio of the pressure to the magnetic field is under 2%. And the power density in the plasma is scaling as that ratio squared. And it also scales as the magnetic field to the fourth power. So, what they're doing in order to be able to make their tokamak is going to something like 17 Tesla, which is a large field. And they're they're doing this because if they exceed that 2% limit, and tokamaks have run some of them up to about 10%, but in order to do, they're trying to not have what are called disruptions. The tokamak has a big current running through it, and sometimes it just disrupts and slams the plasma into the wall, which is a real problem for for what's going on typically. So the FRC is a wonderful device, and the reason that many of us are attracted to it is it gives us that plasma pressure to magnetic field pressure routinely in the lab to what, 90-95%, Sam, right?
Above 50%, maybe 95%, right?
Yeah, and so it depends on your configuration, but you're making much more effective use of the magnetic field. And what that means, Sam, your fields that you have to provide externally must be quite low compared to the 17 Tesla that.
Yeah, our reactor designs look like it's 5 Tesla.
Yeah,
Uh, when you quote 17 Tesla, the magnetic field in a tokamak varies in position by
yes.
a factor of 3. In the center, it might be 10, but on the inner leg of the wall, it might be 20. So the field is strongly varying in the position, and so you have different forces in different parts of it, different requirements on the superconductors.
My next question for you all is, does reduced neutron damage with helium-3 meaningfully simplify reactor engineering, or does it shift the difficulty elsewhere into the,
It's
science
huge.
and technology?
So
Mhm.
among the differences is the thickness of the shielding. In a DT reactor, you need 1.5 meters of shielding around the plasma to protect the components from the outside to absorb the neutron energy to breed the tritium. In a DT helium-3 machine, you might need 25 centimeters of shielding. So you can build a much smaller machine. You have a smaller volume to repair or to replace if that's necessary. You can bring magnets closer to the plasma, and that's very important because it reduces the amount of magnetic field you need, because the magnets, instead of being further away and wasting their energy in spaces not occupied by plasma. So those are some of the reasons why a D helium-3 type FRC would be the right way to go.
And for any of the devices, the one of the huge advantages of D helium-3 over DT, the lower neutron production and the lower energy of most of those neutrons means that you could have the first wall, the first whatever is facing the plasma directly, and what's beyond it, that in a DT system, as I said earlier, is 3 to 5 years is about all it survives. And now you've got a very difficult maintenance issue in a highly radioactive environment. D helium-3 studies we've done, we still need decent data on neutron damage to walls. I mean, we're not even close by a factor of, I don't know, 50 to 100, I think, of what ITER is going to need to show that it can stand. And so you have a full lifetime, which really helps. And of course, these linear systems, as Sam was saying, you have your coils all in a nice row. You can get your piping to them. If one breaks, you can replace it a whole lot easier than these nested coils that you have typically with a tokamak. One thing we haven't mentioned, by the way, is about tritium is that it's got a half-life of 12.3 years, and that means that it does not, there's basically none that's natural in some sense. There's a very tiny amount. So the tritium, okay, and the amount of either tritium or helium-3, if you're going, let's just say a 1,000 megawatt, a big power plant for a fairly large city, 1,000 megawatts electric usually takes on the order of a couple thousand megawatts thermal with the energy conversion. But what you need, and this is the key point here, you need a breeding blanket to create tritium, and basically that's done from lithium. There are some companies, and Helion is one of them, that is trying to do this using DD reactions, but it's that's an interesting problem. I won't try to go.
They want to try to breed their helium-3, but I think it's easier
Yes,
if you just buy it.
I've seen some numbers I can't talk about, to be honest, Andrew. It's
Yeah.
hard, but it might be done. They've had some very interesting results. But the problem with these breeding blankets is, like the materials, there's a whole bunch of options out there that have been conceptually developed, but they've never been tested in anything like a reasonable volume and in a fusion reactor environment with enough neutrons coming in and demonstrating that the breeding blanket works. I suspect, and our group did, our engineers in this area did a lot of work on that at UW. And really, I believe that that'll be solved. But there's this and the materials damage problem for DT are both long lead time problems.
And yeah, so I believe ITER's got a small little experiment just to look at it when they get up and running, right? But they don't have it implemented really. So,
well, and the
Rachel,
UT has put out a contract actually with a Madison area company called Shine to basically do a fusion neutron source at a very low level to look at the science of the breeding blankets. But that's a lot different than being able to really test the engineering.
Rachel, let me try to join together a comment you made at the beginning about the amount of helium-3 currently available on the Earth being 5 kilograms, and what John said about tritium decaying into helium-3. Say a tokamak worked and was breeding tritium, but people found out that it was too complicated to run to breed more tritium for the next machine. You put that tritium that was bred, put it on the shelf, turn it into helium-3, and you could essentially double the amount of helium-3 that was available for FRC type of reactors. So you can make a transition from the helium-3 produced in fission reactors and from bombs to that which you get from a tokamak DT reactor to going to moon mining. So it could be a smoother transition from the very small amount we have now to the larger amounts that would be available from moon mining.
It's a really interesting point. We do have a handful of questions from the audience that I want to make sure we have the time to get to. But before we do that, I'd love to touch just a little bit on the space applications for the utilization of helium-3. And John, maybe you'd like to jump in there on the pros and cons of using helium-3 versus tritium.
Yeah, I've actually published a bunch of papers there. If I might take the stage for a minute, and I know you, Sam, have worked in that area a lot with your Princeton satellite systems company. The first thing I think is, Sam, you talked about constructing the fusion rocket in low Earth orbit. Certainly, we can't launch them from Earth. The fusion rocket is a qualitatively different type of rocket, right? Chemical rockets are going to do a chemical reaction. 90% or so of the rocket is just the fuel and what you it's combustion. It gives you, in terms of meters per second exhaust, on the order of about 4.5 kilometers per second. A nuclear thermal rocket runs hydrogen through the core and exhausts that, can do about 9 kilometers per second. But you can look up with a plasma relatively easily up to 100 kilometers per second or more. And so you can do very high amounts of exhaust, and that means you don't need very much propellant because you've got the fast fusion products. You need the linear devices to get direct exhaust. I think everybody that's looked at it, including way back, John Hilton at Aerojet General had a 1962 or 64 paper where it was a simple mirror that we know the power wouldn't work out, but he could do that. But what you do then with a chemical rocket, you're in orbit now. Oh, by the way, I would do this around the moon, not necessarily around the Earth. I think we're going to be using materials from the moon. The chemical rocket, so-called minimum energy or Hohmann transfer, you're in orbit, you have a big impulse. Let's say you're going Earth to Mars. The rocket goes in a big ellipse. When it gets toward Mars, it gives one more impulse, and it takes 9 months to go from Earth to Mars with a chemical rocket doing that. You can hardly increase that. It's a little faster, maybe 6 months with a nuclear thermal rocket. With fusion rockets, if we get up to a reasonable power density, and I believe we can, and that's 1 to 10 kilowatts per kilogram, we can do on the order of 2-month trajectories. These are one-way trajectories, Earth to Mars, and then on the way back. So with a chemical rocket, you've got 18 months just coasting to get there and then back again, whereas that's about 4 months with a fusion rocket. That's a huge difference, and that really will so-called open the solar system frontier for us. Rockets able to go, it's something like, let's see, Earth to Jupiter with a chemical rocket is about 1,000 days at the same payload rate as a chemical rocket. And if you're going to, you take that even to Jupiter down to about 200 days from 1,000, even at, not a real high kilowatts per kilogram. So let us open the solar system frontier. I think that'll happen hopefully sooner than later if you can get a lot of helium-3 for us.
So let me continue on John's description. Fusion rockets would be very good for any mission from Mars and beyond. And John mentioned the trips to Mars and to Jupiter. Let's take a look at the New Horizon spacecraft, which flew past Pluto in July of 2015. It took 9 years to get there, and it was a flyby mission. It approached the planet, took pictures for about a week or two, flew past the planet, took pictures for another week or two, and then had so little energy stored in its batteries, or it's in its nuclear thermal power source, that it could send back maybe a picture a day or a picture every 2 or 3 days. But if you had a fusion rocket going with a megawatt, instead of taking 10 years to get there, it would take 1 year. And it wouldn't have to be a flyby mission. It could slow down and go into orbit around the planet and then send down a lunar lander. So you could get to Pluto 10 times quicker. You could take 1,000 times more data. You would have enough power on the rocket ship to send back nearly high definition videos of the planet's surface. So for exploring Pluto, it's really exciting. There's another even more exciting mission proposed for fusion rockets, and that's to put a telescope at what's called the 550 AU point. AU means atomic distances from the sun to the Earth. At that position, the sun acts as a gravitational lens, and the 550 point is the focal point of the sun as a lens. And if you put a telescope out at the 550 point, you could use the sun as a very large lens to collect light from exoplanets. And some people have made estimates that you could actually view the surface of an exoplanet with a resolution of 1 kilometer. And so you wouldn't have to fly for 1,000 years to get to the nearest solar system. You can actually use the sun as a lens and a fusion-propelled rocket to place a telescope where the sun's focal point is. So there are
Oh, and
lots of good reasons.
yeah. I should add that the reason this all works is that we have the fast exhaust velocity, but instead of just a single impulse start and end, that it's a continuous thrust pretty much. And that continuous thrust accumulates every second as you're thrusting. And it's that physics is why you get these sorts of numbers Sam and I have been talking about. I think you're muted.
Sorry, I muted myself because I'm getting over the flu and I'm still coughing. Um, I want to ask about there's NASA is interested in putting fission reactors on the lunar surface, and I'm curious if maybe using helium-3 in a fusion reactor might make in situ resource utilization possible on the moon for fusion power. Is that anything that that you've thought about or heard any research about? When we've talked about like this continuous thrust and propulsion using fusion systems, but in is it possible to have a more stable,
I don't
presence
know if the other
power
gentlemen
station
agree
on
with
the
me,
moon?
but I think it's almost folly to the notion of sending that much uranium up on, on a rocket with the risk of raining it down. You know, I don't know that we have a good enough success rate yet
For
to
fission.
for yeah. So that they want to put a standard reactor up on the
Hmm.
moon, and you
Well,
know, it's
yeah, that really a small modular reactor, not a standard reactor like we're running in these huge power plants is, but
right. But
yeah.
but are you comfortable with the risks uh, of
Well,
launching that?
Sam, I have to look up your papers because I don't know how to make things down in that less than 100 megawatt electric level. And but that just means I've been doing this clandestine materials detection stuff much. I've got to look up that. But if you can't get down below 100 megawatts electric, those small modular fission reactors would be good for that kind of power, which for certain things, and especially the things your company is thinking of doing, the LH3 stuff, it needs a lot of power to do some of the mining related
Absolutely.
stuff. Yep.
I want to jump in here just so that we do have a couple of minutes to answer some of the questions people have sent in. We've only got a couple of minutes left here, but I want to give it a little time. One person has written in, I think American Fusion is working to produce a D-helium-3 fusion reactor that will produce its own helium-3 to make a self-providing fuel system, Texatron. Based on my research, they are able to control the heat issue and particles around the walls of machine by magnets' direction of charges. Any thoughts or truth to this?
Well, the idea of using a breeding helium-3 goes back probably 20 or 30 years. It's called the helium-3 catalyzed DD fusion. Uh, your fusion neutrons are reduced from DT by roughly a factor of 30, which is a big improvement. Um, I think that's a possibility, yes.
There was work in the 60s and 70s on so-called satellite reactors that there was a support ratio of about 3 DD reactors that put out lots of neutrons
Mhm.
and the same problems we have with neutrons. But it would then support one D helium-3 reactor with breeding there. And the idea was not to burn the helium-3. Um, and so that's been looked at, but that's been looked at now for what is that, 60 years or so, and nobody's come up with a truly effective way of breeding helium-3.
And another question from the audience. If the over-under in terms of the number of years until a commercial fusion reactor was safely and reliably producing electricity was set at 25 years, would you bet your entire net worth on the over or under 25 years?
I think under at the rate things are going, but I'm not a betting person.
I think
Same
things should be
Andrew.
done. I would put more money in the shorter than 25 years. But if you're talking about making one reactor work versus providing a significant amount of power for the grid, well, it's going to be 100 years before you can make a significant amount of commercially competitive power for the grid. If you simply try to use the terrestrial helium-3 supply to make electricity, it would probably triple the cost of electricity. So that's why niche uses, places, applications where the customers don't care if the cost of electricity is 10 cents a kilowatt hour or $100 a kilowatt hour. That's where I think where you want to go in the beginning. And you want the right kind of customers.
In the long term, I would like to point out that if we can access the gas giant or also Uranus and Neptune helium-3 resources, you measure what they could do burning at the present worldwide rate of energy production in ages of the universe. It is that much of a resource, but of course, you would expect that energy usage to increase over time.
We need the fusion rockets to get there.
Right.
We do need the fusion rockets for sure, and to have the power to process whatever is being done. I mean,
Exactly.
back in 1978, I think it was, the Journal of the British Interplanetary Society had I forgot what it was called now. But anyway, they were talking about hanging a balloon in the Jovian to Jupiter atmosphere.
Wow.
We didn't, at the time, we hadn't had any flybys, and Galileo told us that, not the guy, but the mission, that it's a very turbulent atmosphere there that you'd be hanging that balloon in. But nonetheless, there are big reservoirs of helium-3 out there for eventual use, and roughly the same deuterium content in those planets.
Definitely exciting. Well, that's, I think, the time that we have for today. Thank you all for joining and for offering your insight on this topic. It's been great to hear from you. And thank you to also everybody who joined to listen in to us. And with that, I think I'm going to pass things back to Chris for a moment.
Again, thank you, Rachel, in the panel today for a really cool discussion about the fuels helium-3 versus tritium. I'd just like to end with a slide coming up. So the next in the series, next month on February 18th, same time, we're going to be looking at quantum computers. To run quantum computers successfully, they have to be actually cooled down to 0.01 Kelvin. And ironically, the only way to get it down to that temperature is with usage of helium-3. So we're going to have some quantum experts talking about, if they had helium-3, would that make it better or worse? What are they going to do as a workaround? So join us for that next seminar coming up. And then the month after, to give you a heads up, is going to be a really cool topic. We're going to have space lawyers talking about mining helium-3 on the moon. Not so much about policy, but the legal aspects of that. And then we'll be looking at the economic aspect of helium-3 that'll start in April. So again, thank you for joining. I appreciate your time.